record on this computer. Okay, so we are live. So what we had started talking about in the last class was basically to understand the need of scalable computing and how computer networks evolved as a result of that. And we had started discussing about the fact that initially most of the high load computing that was done based on this paradigm that was known as high performance computing, right? Which consisted of a bunch of very tightly coupled homogeneous nodes that was grouped together. And the goal of that particular architecture was to make sure that it gives us the maximum possible performance that we can achieve in order to perform certain specific application dependent tasks, such as any kind of engineering problem, any kind of scientific problem, any kind of manufacturing or industrial problem, right? But as the internet age evolved, as it came into the picture, the need from high performance computing shifted towards making sure that we are able, using those computer architectures, we are able to kind of support multiple user requests at the same time. And when we say multiple, we mean like millions of user requests at the same time, which led to the development or the proposition for high throughput computing, HTC systems, which thereafter evolved into peer-to-peer networks. And then high performance computing kind of evolved into computer clusters or massively parallel processors. The clusters and the MPPs were of centralized controls, and the peer-to-peer networks were based on distributed control. And they kind of merged into this one single category of computational and data grids. And the evolution of more new computing technologies kind of led to the current day and age where we are using Web 2.0 for different kind of web services that is dependent on the service-oriented architecture, or better known as SOA. And then virtualization enabled the cloud computing platforms, and the interconnectivity between devices that supports some sort of sensing of the environmental features kind of led to the architecture of Internet of Things. So we understood that. We talked about the different design criteria and the different features for HPC and HTC. We kind of introduced ourselves to the different types of computing paradigms, which was namely centralized computing, parallel computing, and distributed computing, and then cloud computing. And we briefly talked about ubiquitous computing, which essentially IoT falls under the umbrella of ubiquitous computing, which is sometimes also known as pervasive computing and stuff like that. So we also talked about the different types of design objectives when we are designing any sort of HPC or HTC systems. And we had kind of concluded the last lecture by discussing the different degrees of parallelism. Okay, and the reason why we touched upon parallelism essentially is the fact that all of these computer networks evolved as a result for a need of scalability. Okay, all the different kinds of computing that is there, the computing architectures or the networking architecture, whatever you would like to call it, the reason behind their evolution is to make sure that it keeps up with the pace of the need of the business and the application demands, right? And as more and more users, systems, or applications, as more and more systems and applications are being developed, new web services are being developed, new users connect to internet every day, there is a need to keep up with that growing demand. And that is where scalability comes into the picture. And if you want to make a process, if you want to make an application, if you want to make a resource scale, okay, then in terms of a technology, what we need to rely on is basically the concept of parallelism. And as such, we learned about the different levels of parallelism. And right now, in this day and age, we are essentially relying mostly upon job level parallelism, which is on the highest level of course granularity, because underneath job level parallelism, you have task level parallelisms, data level parallelism, and then instruction level parallelism. Okay. And beyond that, bit level parallelism, nobody uses that anymore right now, because essentially most of the programs that you write that does not use machine level language or lower level languages anymore, right? So it is either one of the last threes that is used more often than the previous two in a comparative scenario. So now we would like to get into more terms and definitions, continuing our discussions along those lines. We would first like to understand the very subtle differences between Internet of Things versus what is known as the cyber-physical systems, okay? So what happens is, like, there are two different communities in computing that work on CPS, and then the other community works on IoT. And there is this ongoing discussion that, hey, you know, the nature of IoT is kind of similar to CPS, all right? So what the definition of CPS suggests, in order to understand that argument, let us first look into the definition of CPS, what CPS says. Well, CPS essentially merges the three C's of computing, okay? Together, this is known as the three C's of computing. So if you're looking at computation, communication, and control, together these make up what is known as the three C's of computing. This is something that you would like to keep a note of, right? So what CPS architecture or cyber-physical, the notion of cyber-physical systems kind of tells us to do is to take computation, communication, and control, and then merge them together into this one single closed feedback loop, right? Such that you can use the information world, that is the programs that you write and the application that you develop through them, and you can use that to communicate and control the physical world, okay? So a very well-known example of CPS is known as industrial control systems, okay? Which basically deals with the set of programs that you write, which based on certain logic, which kind of delves in the information world, it communicates with all the different industrial materials, all the different industrial control systems, and it operates those industrial control systems, all right? So that is one of the well-known example of CPS. Now, what the contrasting definition from CPS with respect to IoT is that the IoT, or the Internet of Things paradigm, the architecture, it refers to the networked interconnection of everyday object, tools, devices, or computers. So when we say IoT, the generic umbrella of IoT, it can encapsulate any type of device, right? It could be your cell phones, it could be your coffee machines, it could be your smart fridges, it could be your smart watches, it could be all your sensor nodes, it could be any kind of autonomous vehicles, right? So anything that has some sort of sensing capabilities, and even if it doesn't have sensing capabilities, then you can still interconnect it to the network architecture for control purposes. And then the interconnection of these devices with each other and with the internet, okay, kind of encapsulates the notion of Internet of Things, right? So if you understand the differentiation, or if you understand, if you capture the conceptual definition of what is Internet of Things paradigm, and then what is the cyber physical system paradigm, then the question that you need to ask yourself, that is there any overlap between these two, or are they completely different concepts altogether, and as such they should be treated differently, right? So that is a question for your self-reflection and your self-thinking, that if IoT refers to the networked interconnection of everyday object, tools, devices, or computers, right? And typically these communications or interconnections can be either mostly through a wireless network, and in some situations, it can also have a wired connection as well, if you're talking about like desktop computers and stuff like that. But nowadays, desktop computers can also use wireless communication, right? And if CPS is basically the interaction between computational processes and the physical world, then is there essentially any difference or any overlap? Difference is a very strong word. Can we say that is there an overlap between the conceptual notion of IoT versus CPS. What are your thoughts? Anyone?
I'm not sure, but IoT kind of seems like a superset of CPS almost.
Okay. Anybody else?
I'm sort of building off that. CPS seems to be like an industrial subset of IoT.
Okay. What else? Anybody else? Any other thoughts? No? Okay. So initially, when these notions came out into the picture, right, or when it was proposed, that was along the early 2009, 2010s, when smartphones kind of erupted in terms of their popularity with the introduction of the iPhone, and then eventually Android phones coming up with their own cell phones as well, Samsung and others. The notion of IoT and CPS was different, right? And that goes back to the discussion, because the idea of CPS was specifically used for industrial control at that point of time, right? So it was writing a bunch of program which had certain logic and which kind of directly communicated and controlled with the physical hardware of the industrial systems, right? And IoT was mostly basically, say, connecting your smartphones or your fridges and stuff like that as they came into the picture with each other, right? So if you want to look at the very core difference, of course, there is an overlap. It depends on the nature of implementation that you're doing. If you are taking some sort of IoT paradigm, okay, let's say smart home. So if you think of smart home as an example, smart home falls into the category of IoTs, right? Most of you are familiar with this fact that you can have a Google Nest device, or whatever you call it for Apple. I think it's called an iPod or something. No, not I. Everything is I something. So I will just say I something. So if you have these Apple devices, if you have the Google devices, if you have the Amazon devices, and then people are coming up with these things such as smart plugs and stuff like that, essentially all of them kind of falls into this branch of developing a smart home, where you can discover services, that is what devices are connected and how you control them. The interconnectivity of smart home in itself falls within the branch of IoT, right? But then if you start writing logic, if you have used even your phone assistant, right? They have some of these smart logics where you say that, oh, if your morning alarm rings at 8 a.m., then your Google Assistant or whatever, Siri, would kind of tell you about the news and stuff like that. Would you consider that as a CPS application?
No.
Why not?
Because that solves a human, like the home purpose. It's not for industry. So the difference is like
okay, pay attention to this particular notion. CPS is the interaction between computational process and the physical world. Industrial control system is a well-known application of CPS. So it doesn't mean that CPS is directly proportional to industrial control system. CPS, in its core ideology, means the interaction between computational processes and physical world. Okay, so as a result of that, if I have a smart thermostat which is integrated within the smart home and it controls my HVAC unit, which is a physical world and a physical device, right? If the logic of my application communicates with my smart home HVAC, and it either turns it off, turns it up, turns off the fan, increases the temperature, reduces the temperature based on some logic that you have written for your application that is running on your smart thermostat, right? Would you consider that as a CPS application?
Yes. If we're going with the physical interaction being the differentiator, yeah.
Right. So keep this in mind, that the subtle difference is that any IoT application can be a cyber physical system application if there is computation, communication, and control that is originating from the computational processes and going into the physical world, right? But if we are specifically talking about the network interconnection between any type of devices, right? That is why in IoT, the T stands for things, right? It could be anything. As long as it can communicate, it has some sort of wireless communication medium, uses Bluetooth, radio frequency, wire, Wi-Fi, any other communication medium, wired communication medium, as long as you can interconnect it. That ideology of interconnection is basically Internet of Things, right? However, when within this interconnection of things, you use computational logic and that communicates and interacts with the physical world, right? That falls into the notion or the paradigm of cyber physical systems. Please keep in mind that CPS is not specific to industrial control. CPS, the incorporation of CPS or the notion of CPS in industrial control is very evident, right? But that doesn't mean that CPS does not have implications in other day-to-day applications, right? So something to keep in mind. All right, so again, to recap what we just discussed right now, IoT emphasizes on networking, okay? Whereas CPS emphasizes on the exploration of any type of VR applications in the physical world. This is one example, but basically what we are saying that if you develop some sort of application which merges, and this is the important part here that you have to pay attention to these words here, it merges computation, communication, and control into a closed feedback system between the physical world and the information world. Okay, so that is essentially the differentiating factor. That is what you will have to keep an eye out, that an IoT can become a CPS if it has this following characteristic that kind of defines the notion of CPS. However, if you're mostly focused about the interconnection between the devices, that will be either communicating with each other or communicating through the internet, then that just falls into the umbrella of IoT, okay? So now, how does the communication take place, right? We are talking about the interconnection about different devices and stuff like that. We're talking about merging communication, computing power, and things like that. So what are the different well-known or commonly used options when it comes to interconnections? Well, the first one is something that you are all very much familiar with, and it's known as the local area network, okay? Or better known as the acronym LAN, right? But in addition to LAN, you also have the option of WAN, that is known as wide area networks. And then in addition to that, there is sometimes you have global area network, okay? Or which is also as an acronym known as GAN. Okay, so an example of a local area network could be one of the computing labs in Oakland University. Okay, even the entire interconnection within Oakland University, if it happens, or which it does happen, at least the closed network does happen using Ethernet, that falls into the category of LAN. Okay, however, let's say we have OU, and then we have, I don't know, Eastern Michigan, and you have UMich, and then you have Western Michigan, MTU, and things like that, right? And they are now interconnected with each other. Then that interconnection will fall into the category of a wide area network, right? Or even if you think that OU has, let's say, two campuses, one is the main campus that is there in Auburn Hills / Rochester Hills, and then you have the Macomb County campus, and if you interconnect with that, that will also fall into the category of wide area networks. But now if you say that you have this whole network, like this cluster of computers of all these universities that are in Michigan, and then you are trying to interconnect that to, let's say, Indiana, and then with respect to Illinois, and then with respect to Ohio, right? So if you're doing this, something like this, then that will fall within the category of a global area network. Okay, so that is basically the communication capabilities of these different computers, right, in terms of the interconnections. But now communication in itself is not sufficient. Okay, the 4 important resources in terms of computing that you need to provide to any kind of user, let's say any kind of setup that you're making for any company, or if you're a user and you're trying to use some sort of utility computing or service computing, if you remember that definition, we had talked about that last time. So you basically have compute, okay? Then you have storage. Then you have networking. Okay, and the reason why I mentioned compute is because this can be then broken down into the number of CPU cores that is being provided and the processing power of this CPU core. So together, these just fall under the category of compute, right? So if you look into cloud computing, they will mostly talk about what do you need, right? What do you want to rent out from the cloud computing architecture? And they will say that, okay, you have the options of compute, you have the options of storage, or we will just provide you with networking capabilities that you can remotely connect to some of our applications that we are already providing, right? You don't have to develop anything of your own. We can just provide with that, okay? So here, when we are talking about LAN, wide area networks or global area networks, then we are talking about the capability of networking, right? And compute in itself are the nodes. So we're not calling them computer as such. They can be many different types of computers. So these computers, when it is connected across these networking features, right, together kind of captures the resources of compute and network, right? So what remains? The capability that remains to be provided or kind of implemented if you're making your own private cluster is the idea of storage, right? So now you can always buy these hard disk drives in order to kind of create the storage medium, but that storage medium needs to be accessible, right? And they don't fall into the typical networking interconnection of LAN or WANs, right? So what we do there is basically we implement what is known as the storage area network, that is known as the SAN, where the servers that you have within your computer clusters or computer networks, they are directly able to access the storage mediums that you have implemented. So that is the first option in order to access your storage. The second option is known as a network access storage, or sorry, the network attached storage, or better known as NAS or NAS, right? Not the artist, but the computing structure, the computing technology, okay? So when you use NAS, then essentially what can happen is that the client hosts can basically bypass this communication transit from the server then to the network storage and directly or remotely access the disk arrays, okay? So one of the typical examples that I don't know if you have used it, but is very much available, is that Oakland University provides storage, right? So if you VPN into the OU domain, you can either choose to directly connect to this storage without having to be present within the OU domain. So you're remotely accessing the OU storage. So this OU storage is basically a disk drive which has been implemented using the idea of network attached storage, right? So as a client, right, you can simply connect to the OU storage instead of going through their VPN, getting into their domain, and then accessing the network storage, which will basically be an example of storage area network if you use that kind of protocol, right? So basically, these are the different types of interconnections that are available, right? The other thing that kind of enables scalability is the idea of maximizing resource utilization, okay? So scalability is all good, right? But the problem here is that if you keep adding resources, but if these resources are basically underutilized, then you are not utilizing the amount of resources that you have added. And as a result of that, you have this cascading problem that you are not really enforcing scalability into the picture, right? I hope you understand the logic of our discussion of where we are going is the fact that, okay, when we are talking about scalability, we are saying that, oh, we add more nodes to the computer networks and we bring in all of these different interconnection technologies. We bring all of these different architectures of HPC, HTC, peer-to-peer networks, massively parallel processors and stuff like that. But if you add all of these resources in order to keep up with the demand, but if you do not effectively use these resources or even efficiently use these resources, then the whole purpose of scalability is kind of destroyed, right? You're not effectively utilizing your resources. So the solution in order to address this problem of underutilization of resources was formulated in the form of what is known as virtual machine architectures. All right. So here in this particular illustration, you have 4 different cases, right? The very first case is a case where you do not have any kind of virtualization. So you have a single integrated operating system, right? That is running on top of a dedicated hardware. And on top of those kernel, that is the operating system and the hardware, you are running your software applications. Okay. So now let's say, and this is a very simple motivation to understand, is that on this computer right now, the computer that I'm using, or you can even think of your own computers, I'm running how many applications? I have, let's say, a Zoom running. I have PowerPoint presentation. I may have some sort of browser open and things like that. Okay. Now let's say my particular system, let's assume, has 16 gigabytes of RAM in terms of CPU memory, right? It has somewhere around 3.2 gigahertz of processing power, and it has around like 2 TB of storage. Just assume this, right? So now if I'm running Zoom, PowerPoint, and a browser, will it use effectively 16 gigabytes of memory? And the answer to that is a glaring no, right? And that is what we mean by effectively saying underutilization of resources. If I had taken such kind of nodes, such similar specification nodes, and I, let's say, buy 100 of these, right? And I connect them using a LAN and stuff like that, apply some middleware logic in order to make sure that I can provide these resources to, let's say, students so that they can run their application. But everybody gets one machine, right, to run their application, whatever, for their project purposes, doing the homework and stuff like that. Okay. And even if you assume that you are running some kind of 3D modeling applications, if you're running something like a MATLAB, processor heavy applications, right, you will still not hit this benchmark of utilizing the entire memory. You will not get there, right? You probably have to use some very high threaded application in order to hit that limit. Okay. So you can effectively understand the motivation behind why we need virtualization. So now what we are saying that instead of using this dedicated setup, what we can do is on top of the hardwares, instead of installing a dedicated operating system, what we would want to install is known as a hypervisor, right? Or a virtual machine manager, or a VMM, right? Hypervisor is an example of a VMM that implements. So what this VMM is going to do is it's going to allocate a subset of the resources that is available from this entire hardware and then provide it to different users. So this will not only take care of the utilization of the idle resources, and this is the important keyword here, that is idle resources, but it will also increase scalability. Okay, so now let's take an example that, let's finish this architecture first. So on top of the hypervisor, which is effectively responsible for managing the case of virtualization, that is, it's going to create the virtualized resources and it's going to provide that to the users who are going to use those resources. So on top of that, you remove this operating system, dedicated operating system, from the kernel side, put it on the application side, call it what is known as a guest OS, and then any kind of application that you specifically want to run. So a very simple example would be, let's say, I am the administrator of this previously discussed machine, right? And I say that now I can, using my VMM is basically the interface that will let me create the allocation of virtual resources. Please keep this in mind. That is what the definition of the responsibility of the hypervisor is that they are basically the administrator of the resources, right? So now using the VMM, if I am the administrator of this particular machine, I say that I'm going to take this whole computer and I'm going to break it down into, let's say, 2 gigabytes of chunk, right? Or for computers these days, we can just say 4 gigabytes of chunk, depending on the nature of applications that we plan to run, right? I'm going to chunk out the processor uses as well through the hypervisor. And I'm going to allocate, let's say, 2 gigabyte of available storage. And I'm going to create 4 such chunks. And I'm going to put it on top of my kernel, right? And then whenever a user comes, let's say if I want to use my Zoom, PowerPoint, and browser, that is very much doable in 4 gigabytes and 2 GB of storage, okay? So then I can support, hypothetically speaking, a net total of 4 users, and I can effectively reach the maximum capacity of resource utilization on this one machine, right? So now if we go back to this earlier assumption that, oh, I had purchased 100 such computing devices, then effectively, hold on, Brendan. So effectively, I can utilize all of my resources, okay? So there is a question in chat, which is, would you utilize an API to connect to your apps to a VM, or only for connecting to a virtualized server or a database? Okay, so would we use an API? Every time I go out of this, it goes away. Okay, so would I use an API to effectively connect to the apps that is running on the VMs, or would I just use it to log in to my virtual machine and then use it, or then deploy any kind of applications? Would somebody like to answer this question? Does everybody understand the question? Thumbs up, thumbs down.
Could you repeat the question?
So the question is, so here you can see that we are running different guest apps, guest OS is there, and we are creating virtualized instances. So this could be one virtualized instance. This is one virtualized instance, one virtualized instance, and one virtualized instance. Each virtualized instance, probably, hypothetically speaking, let's say has 4 gigabytes of compute, 2 gigabytes of storage, and then a portion of the processing power that is enclosed within the 4 gigabytes, and the total hardware is around 16 gigabytes, right? So if a user connects, okay, so let's say a user is trying to access this resource, so they are basically going to use an application interface, okay, or an API. So would they connect to an app, or would they log into the virtual machine and then deploy their apps?
They
I
need
guess
to
the
log
VM
into the machine and then deploy.
Okay, so talk to their machine first. So let's say option 1 and option 2. So one suggestion was it will be option 2. Think about it for a second, reflect upon it. And I will give you the hint of where the actual answer lies. It lies in what is called service models. Okay. The whole nature of virtualization leads to the paradigm of what is known as service computing or utility computing. So that means as an administrator or as a service provider, I'm providing my computer as a utility to users, right? So there are many different ways in which I can provide this utility. What do you think?
So like you could have a remote connection, and so you don't need to physically be in the, I guess, in the computer that's hosting it.
Not physically, but would you log into a session of a computer? Like, let's say when you open your own computer, right? You see welcome to Windows, whatever, log in, right? So when you're remotely connecting to a virtualized instance, you basically have an API, right? It's in the form of either secure shell if you're using Linux or Mac, or what is known as the remote desktop software if you're using Windows to connect, right? So this is basically the API. Using the API, if you directly log into the virtual machine, you will get that welcome prompt like, hey, hi, what's up? And then you log in. And then when you log in, you see a desktop similar to what you see in your personal computers, right? So that is what one option of the question is that Brendan is asking, is that when you remote connect, would you log into your virtual machine, or would you connect to the apps that is loaded on the virtual machine?
I think it's the apps that are installed on the virtual machine.
Okay.
I think we just connect to the virtual machine and then we perform the operations that we needed.
Okay, so here, okay, again, here is my question. Is this a mutual exclusive question? That means that does it needs to be either or can it be both depending on the situation?
It can
Or
be
one of
both. It can be both, I think.
Yeah.
Yeah, depending on the utility that you said,
Yes.
depends on the depends
Right.
on the conditions.
Right. So essentially, like I said, the hint to the answer lies behind this, and the utility and the service are provided in three different ways. The first one is known as infrastructure as a service, right? So the moment when we say that the service utility that me as a user I'm trying to connect to, right, is infrastructure as a service, then you log into the virtual machine. You have your own particular machine. As a user, you don't have an idea of the physical instance, but you are basically interacting with a platform that feels as if it's your own personalized computer. And there you can deploy your own apps. There you can run any kind of program. You can deploy your web servers, you can deploy your web application, you can write your own machine learning code, whatever. You can store your data. So essentially you are using an infrastructure resource remotely, so to speak. And that is the power of virtualization. Now, if the service model kind of goes into, let's say, platform as a service, which is the second service availability, or let's say software as a service, for example, Google Docs or Gmail, then you're not logging into the virtual machine, but you are directly connecting to the apps that is running on some virtual machine, which you are not aware of. Make sense?
Yes.
Okay, so please keep this in mind that it is depending on the type of utility that you are trying to access from your service provider. The service provider, essentially, we keep on saying cloud because that's the most prominent one, right? But it could be some proprietary service provider as well. Even OU can provide you connection to different machines, infrastructure. It can provide connection to different platforms. And it can even provide you connection to different softwares that is running on their machines, right? Google Doc has to run somewhere. That application is not running. When we say on the cloud, it's not just floating around, right? It is supported by something, right? So that is what you have to keep in mind. So this is one of the architectures that is known as the very basic or native virtual machines, right? There are other architectures for virtual machines, right? Where you can have the hardware, but directly on the hardware, you can deploy your own OS, right? And on the application level, you can install a hypervisor, and then you can manage the different virtualization instances, which you can give to different clients or different users of your organization. Okay, so this is more of a very large scale operation. When you're thinking of a hosted operation, you don't do it for an individual basis. For an individual stuff, you mostly stick to native VM. Sometimes you can go to dual mode, but hosted VM, you have to think that, okay, think of hosted VM in this way. It's not actually implemented, but there is a presence of it. You probably might not have had a chance to experience this before, but OU uses its own versioning of Windows software. Windows operating system. Okay, which means it's not your typical Windows Home or Windows Pro. It's a Windows operating system that has been licensed specifically for the purpose of Oakland University, right? And as a result of that, you don't get any kind of proprietary activation key. You need to be on the OU domain. If you are not on the OU domain for an extended period of time, basically that will get deactivated. Okay, case in point here, activate Windows. I don't know if you guys can see this, but this is what is happening. Okay, so that is a host OS. Now, if you are using such kind of host OS, and as an administrator, you want to create virtualized instance on, let's say, a cluster of such computers, then you can use something like a hosted VM, right? Where I'm providing you with the OS, okay? And that OS remains as such. And then I break that into chunk and then provide that to different users of my organization, okay? Whereas in the dual mode, it's a combination of native VM and hosted VM, where you can have the virtual manager running here, but you can also run your own host. And then in the application level, you can create your own instances of virtualization by deploying separate operating systems. Okay, so essentially, if you want to kind of wrap our head around the whole, if you want to summarize this virtualization concepts, then virtualization is all about breaking down the different layers of system implementation. Okay, so at the very bottommost layer, you would have the hardware. Okay, on top of the hardware, you would have the operating systems running, right? Then you would have your application, and then you will have your user and storage. And this is a funny thing. Storage is necessarily not on the user level, but it's in somewhere in between the application and the user. So we are going to rewrite this one more time. Does my eraser works? No, it only works for PowerPoint mode. Okay, so we're going to remove this and we're going to say the storage is somewhere here, and hopefully I can finish my drawing. So now the whole idea of virtualization is basically to separate. If you think of an individual single consolidated PC or laptop, then all of this are tightly coupled. Okay, you have your own hardware, dedicated hardware running your single operating system. You can run your applications. You are the only user which is interacting with your application, and the storage is directly connected to that hardware, right? But when you think of virtualization, then we want to separate all of these, right? But here there is a slight subtle nuance, okay? That storage kind of is present both on the user side as well as the application side as per needs, okay, wherever you need it. So that means if you're remotely connecting to a virtual resource, you can pull the data, store it on your machine if you have the capability to store those data sets. Otherwise, if your task is not data intensive, let's say, for example, your Google Drive storage, right? So that is an example where the storage is on the application layer, right? So that is another example. So here your hardware can be from anything, right? You can deploy any kind of operating systems, okay? This is a little bit tricky, okay, because Apple being Apple, everything is very hard and proprietary. But what people generally do is they take Linux or Unix, okay, and they create these variations that is specific to their application. So for example, if you're thinking of AWS does not use directly Linux, okay, the core Linux operating system, but it has something that is known as an Amazon machine instance, which is a variation of Linux. That is the whole skeletal framework is built on top of Linux, but Amazon has given its own kind of firmware to it in order to create an image of Linux that can be deployed for operating system purposes, right? You are very rarely going to see this, okay? Love it or hate it, it really creates some problems from time to time, okay? Application wise, you can either deploy your own applications or you can deploy your own platforms and stuff like that. And well, the user is happy, okay? You can satisfy whatever user you have if you're doing this, okay? So that is the whole idea of virtual machines, right? But remember, the goal of virtual machine is to prevent this underutilization and thereby further supplementing the improvement of scalability. Just using virtualization does not take you to cloud computing. Okay, even though here we had discussed that the notion of virtualization led to the cloud computing, but it's just not there, right? It's just not there. It's one step behind there, okay? Anybody would like to take a wild guess that what you need to supplement virtualization with in order to actually take computational grids or computer clusters to cloud computing? You don't have to answer now. You can think of this answer, but that is an effective step that you have to keep in mind, okay? All right, so what are the benefits of VM then? If we look at a summary, well, we can use what is known as multiplexing, okay? Multiplexing means that if in a dedicated instance, a given kernel and an application is supposed to utilize the resources of that particular kernel, what virtual machines enable us to do is that if this particular hardware gets overloaded, then I can take some of these virtual machines and I can make them migrate and run on different applications, okay? Or just utilize the resources of this hardware, and this application is originally running on this first hardware, but I can kind of utilize some of these resources. There is also some interchange between the apps as well. So if there are two different users utilizing this hardware, if one of the user kind of reduces the intents of their intensity is not a word, but you get the idea. If their application becomes less load intensive, then this app becomes more load intensive, then some of the hardware that was allocated to them can be taken away and then given to the other person. So that is the whole idea of multiplexing, which kind of is enabled by VMs, okay? We can provision virtual machines based on what others are using. So a case in point example that we were discussing here is that as a user, whenever you come to, let's say, Amazon Web Services and you want to deploy a host operating systems, you don't have to go to the Linux website and download their image and then write your own firmware on top of it. There is an image machine instance that is already created for you, right? All you have to do is select that and load it across multiple virtual machines, right? So whenever you go to this vendor or this service provider who is going to provide you with all of these different services, you can simply take the image of a virtual machine and then you can load it as an image to another virtual machine instance, right? So that is known as provision, that whole idea, okay? You can suspend any virtual machine instance and save it on your storage, okay? So for example, if you have created your own personalized configuration, right, and you like what you use and you want to retain that for future uses, but the utility of that particular virtual machine is done for the time being. Remember, it's utility computing, right? So you pay as much as you use, right? And you pay even more. That's quite ironic. But most of the services, if your service is running idle, right, and you don't use the resources that has been or that you have asked for, you get charged more, right? Because the service providers don't want some kind of hardware being locked by you unless you are actually paying for a dedicated instance. Okay, we will come to that later on when we get to the CC part, but please keep this in mind, right? So you always want to what is known as suspend your virtual machine instance, not destroy it. If you destroy it, then it's gone. Okay, destroying or purging is a different concept. That means you're destroying the whole or deleting your whole virtual machine image instance. But if you're suspending it, that is kind of like putting your computer to sleep mode in a way, right? You can take this whole virtual machine instance and you can simply put it in persistent storage, right? And whenever you come back, you can take this, put it on the same machine, allocate it to different machines, different regions, wherever you want to take it, okay? And finally, you have the capabilities of live migration, okay? As your virtual machine instance, so we are going to call this VMI from now on. Okay, these individual instances that you see in green and yellow, we refer to them as a VMI or a virtual machine instance. Okay, so a virtual machine instance is basically a combination of the applications that you have deployed on a host OS that has been allocated to you by a hypervisor or a virtual machine manager running on top of some physical hardware that is unknown to you. Okay, so this VMI, you can take one VMI, and as that VMI is running, you can take it and host it on another complete different instance of VMIs. Okay, it can be on the same hardware. Here it shows a separate hardware to kind of emphasize the live migration purpose, but you can do it on the same hardware as well. I can migrate it here. I can migrate it to a different instance. This is not fully in your control as to which hardware you choose. You don't have full control over it. Okay, not fully controlled. Unless you pay for what is known as a dedicated instance, then you know that you have rented out a particular hardware just to host your applications. Okay, otherwise, if you are doing, which generally is the whole idea of cloud computing, that is known as a multi-tenant architecture. Okay, so that is what mostly cloud computing follows, which means that the VMIs of multiple users are co-located on a single physical instance. So that is known as multi-tenancy. Okay, that's the concept of multi-tenancy. Then you do not have the control. So when we say doesn't have fully control over it, that is when you're using public clouds, right? But you have the option if you're a very large scale organization, and if you want to rent out public resources or private resources from the cloud for, let's say, a period of 1 to 3 years, sign a contract, so to speak, right? Then you can opt for what is known as a dedicated instance, right? Which will guarantee that you have a specific physical instance allocated for your purposes only. Okay, so everybody understands this? Yes?
Yes, Professor.
Yeah. Okay, so the final slide within this chapter is basically a classification of parallel and distributed computing systems, right? So I'm not going to read them out. I just leave them out for you to read them. So basically we have the distinctions between computer clusters, which is basically a child of high performance computing, peer-to-peer network, which is basically a child of the paradigm of high throughput computing, data and computational grid, which is basically P2P computing that is married with the concept of computer clusters. Okay, when you have interconnectivity and file sharing between computer clusters, they essentially become either data or computational grid, and then the evolution of cloud computing. Okay, so read this up. There are different features. This is a good to know aspect, and there are some examples as well at the very end. But the core question that remains that we want to ask here, where did I ask it? I asked it somewhere, but I will just write it here. Okay, there is one question that I would like you all to ponder about, is that in that very first diagram, it said that from computational grids, so computational grids or data grids, if you apply the concept of virtualization, and we now have a brief understanding or a high level understanding, we are also going to discuss virtualization more in depth in the coming chapters. It gives the rise to internet clouds. We can stop calling internet, we'll just say cloud, okay, for the time being. So now what I am telling you is that this is not enough. This is not the whole core concept of getting to cloud platforms, right? There is one more feature or one more design criteria that is very important in conjunction with virtualization that you need to introduce in order to finally design cloud computing architectures, right? So think about that. That is going to be your self-reflection task. It sounds like a philosophy course, but hey, it helps, okay? Improves your thinking. So I'll ask this question again in the next class. So please think about it. Like, what is this missing feature? Okay, so do some research, try to find it out, okay? All right, so we'll take a 5 minutes break. It's 6:30 right now, and stretch our legs, get some drinks or whatever, And then we will resume with the next chapter, which is the introduction to computer clusters at 6:35 p.m. sharp. Okay, so right now it's 6:30. We are going to start at 6:35. So I'll see you all in about 5 minutes time, and I will pause the recording. All right, so now that we understand the basics of the need for scalable computing, the different types of computing paradigms that we have, right? Let us get into a little bit more in depth about the idea behind what is known as computer clusters, okay? So the very first concept that we want to understand is why use computer clusters, all right? So if you remember from the flow diagram that we were discussing, initially in the 1960s, right, the whole idea of computing was high performance computing. And then high performance computing gave way to what is known as massively parallel processors, or MPPs, and the idea or the notion of computer clusters, okay? And initially, most of these were centralized computing, but later on, as time progressed, okay, this centralized computing gave way to distributed computing as well, okay? So then the question was, why was the utility of just relying on HPCs, which used mainframe computers or supercomputers, not enough? Okay, so for that, we need to first understand the whole construction or the architectures of mainframe computer and supercomputers, right? So this is kind of like a no-brainer. We all understand supercomputers and mainframe computers were these very huge computing devices that was kept in a single room that had a lot of computing power, yes, no doubt, but it did not support the effective idea or the effective motivation of scalability, right? Because every time you wanted to kind of scale up the resources of a mainframe computer or a supercomputer, then you would have to kind of add that entire device again, another instance of that device. And that became very costly, not just in terms of acquiring the resources, but housing those resources as well. That is, in terms of its maintenance and in terms of its management, it became effectively very difficult, right? And also, the notion of centralized computing created this one bottleneck, is that depending on where you are, if you're trying to remotely access any of these HPC resources, right, you would have to remotely log into wherever that is geographically located. So for example, if you go to Florida or Texas now, right, and if your mainframe computer or your supercomputer is located in, let's say, for example, Seattle, right, just hypothetically speaking, then you can understand the latency of your communication, of your remote communication, is going to go very up. Now, if you go into a global scale from here, if your mainframe supercomputer is located in Seattle and then you go on a business trip to somewhere like Japan or in the Asia Pacific region, then that kind of creates the overhead of latency even further, right? So it was not sufficient when it came to scalability just to rely on supercomputers and mainframe computers. And of course, it also had the issues of the underutilization of the resources that was being provided. And it was very application or domain specific, right? You cannot do day-to-day business tasks of supporting, let's say, user queries, internet queries, search queries on a supercomputer or mainframe computer. Those architectures was not just meant for that, right? Then people came up with massively parallel processors, okay? So if you pay attention to the architecture of massively parallel computers, then instead of uniprocessors, okay, which was at the time what we were using, right, back in those days, back in the heydays when we were coming up with these systems, right, this was not sufficient when it came to scalability, right, because it had a single processor and it executed most of the tasks that you would run on them in a serial fashion. And you know that serialization or iterative execution of tasks is an enemy of scalability. And that is why the whole notion of parallelism, I'm just going to write it like this, came into the picture, right? So in order to support parallelism, we can no longer rely on uniprocessors, right? So there was a shift in the architectural paradigm, which suggested the use of dual core processors, and later on that dual core shifted into multi-core, right? And essentially the development of such hardware chip technologies of dual core or multi-core processors, that is at later stage was also supported by this parallel GPU units or graphic processing units as well, came into the picture. That led to the incorporation of MPP architectures. Okay, so the way the MPP architecture looked like is within a single unit, within a single CPU chip, there were multiple processors. Okay, so let's say we have 4 processors. Each of these processors were associated with what is known as their own private cache. Okay, and these were known as L1 level cache. It's the most expensive, but the most fastest cache. Okay, and right now we are talking about computer architecture a little bit in order to understand how the evolution took place. Okay, now on top of that, within the CPU chip, there was also an L2 level cache, okay, which was a little bit slower than L1 level cache, but it was also cheaper than L1 level, right? And all of these processors shared this L2 cache, okay, within the CPU chip. And this all lies within the CPU chip itself, right? And they have some kind of interconnection bus in order to communicate with the L2 cache and thereby sharing some level of storage with each other. Outside of the CPU chip, right, within the primary memory, you had another L3 cache, which was the slowest among the 3 cache levels. So cache has 3 level hierarchies, L1, L2, and L3. And this was thereafter again shared by the CPU itself, right? If there was any kind of singular task. So this was the whole architecture of massively parallel processing units, okay? And as you can see from this diagram of this architecture itself, these setups were very tightly coupled, okay? And this were hosted in this individual machines or this individual systems. That is, it came on a singular hardware, right? So we can categorize this whole setup, we can bundle this into a single given hardware, right? So that was the first step towards the replacement of mainframe and supercomputers, the proposition of MPPs, right? But that was not sufficient enough. There was one more step that we needed to take, and that was the cost factor. Okay, we mentioned the fact that in order to kind of scale up any kind of system architecture that uses mainframes or supercomputers, it was very costly to add another unit of it and then effectively either acquire it, maintain it, and manage it, or then house it in different physical or geographical regions, right? So MPP was then shipped into what is known as, or what we commonly call as commodity hardware, okay, which was quite cheap to acquire. It was very smaller in size when you compare them to your mainframe and supercomputers. And that effectively came in the form of our PCs and desktop. And the interconnection of these PCs and desktop that probably incorporated the MPP architectures, that led to the development of what is known as computer clusters. Okay, so essentially, we used computer clusters that incorporated the notion of massively parallel processors in order to replace the older generation supercomputers and mainframe computers that was dedicated for specific applications and was used for high performance computing. Okay, so overall, the idea behind computer clusters is to basically enable scalable parallel. Parallel is coming from MPP, and distributed computing is coming from computer clusters. Okay, And the scalability is coming from the usage of commodity hardware. Okay, so please keep this in mind. These are the three essential. This is how we are actually implementing this. Scalability is coming from the incorporation of commodity hardware such that you can acquire these resources in a cheap fashion, host them easily, maintain and manage them. The parallel part of computer clusters is coming from the incorporations of MPPs, and the distributed computing is basically coming from the notion of computer clusters. And that is how together, using all of these features, we were able to replace the older generation HPC incorporation that used supercomputers and mainframe computers. Okay, so what are computer clusters then? It is basically a collection of interconnected standalone computers. Most of the times we are going to interchangeably call the computers as nodes. Okay, please keep in mind that we are going to interchangeably use the term nodes within computer clusters, and that is basically going to represent computers itself. And just the interconnection of different nodes does not constitute a computer cluster. This is a very important distinction. If you have, let's say, 100 machines which have 4 gigabytes of memory, okay, that does not mean that if you simply interconnect them using Ethernet LAN, it will result in an effective system which will have a total processing power of 400 gigabytes. This is not going to happen. You need some techniques, you need some sort of schemes, okay, design criteria, in order to make sure that this interconnectivity will allow the computers to work collectively and in a cooperative fashion, which gives this illusion of single integrated computing resource pool to the end users. So that is important. Otherwise, it is not a cluster. It's just an interconnection. Okay, you can just communicate between them. They are literally not providing the collective resources. So what is important for a computer cluster or for an interconnection of computer nodes to be called a computer cluster is to make sure that they can work collectively and they can work cooperatively to provide this illusion of a single integrated computing resource pool to the end users. Okay, and as a result of that, if they can perform collectively and cooperatively, they should also be able to sustain and therefore support what is known as job level parallels. Okay, so those are essentially the features of computer clusters. So what is the basic architecture then? Well, you have the interconnection. That is the first part, right? So you have, let's say, some PC or workstation, which could be either present in the same geographical location or it could be present in a geographically distributed region. There is no restriction on that. It depends on the design of the computing architecture that you're trying to implement, right? All of these PCs and workstations will have its own NIH, that is its network interface card, okay, or NIC sometimes it's called. It will have its own communication softwares, okay, its Ethernet port or its wireless communication module, so on and so forth, whatever you're using. And they will communicate through what is known as a network switch, okay. Typically, these network switch or some isolated clusters are thereafter connected using what is known as a gateway device. Okay, and a typical example of a gateway device is essentially your routers. All right, so here you have a router which will allow you to connect from one cluster to another cluster. On top of that, on top of these interconnected machines, so this is just the interconnection. Okay, so this definition that we looked upon, the first point here, which is saying that a collection of interconnected standalone computer, this is the part which kind of facilitates that. Okay, on top of that, now we will look at the second bullet point of the features or the definitions of a computer cluster, which says that it should be able to work collectively, it should be able to work cooperatively, and provide an illusion of a single integrated computing resource pool. So that is effectively implemented by this second subset or the second platform, which is known as a middleware. Okay, and the middleware is what is responsible for implementing the different techniques that will allow what is known as an SSI, that is a single system image. Okay, in short, this is known as SSI. Okay, and then it will also work towards improving the availability of this infrastructure. Okay, that is to make sure that this infrastructure is accessible by end users, even in the presence of different faults, even in the presence of different failures. Okay, and then on top of this cluster architecture, users can run their sequential applications. Okay, the day-to-day application, the local application that will utilize some of the resources, or they can run some sort of parallel applications as well. And there is a platform that will allow you to kind of implement those parallel programs, right? Or develop those parallel programs and then submit those job tasks to this computer cluster. Okay, so that is the overall architecture. So what are the benefits then? Well, if you are able to successfully use and implement and then use a computer cluster which has MPP architecture, then you will get very good scalability, okay, at a very cheap cost. So that is important. Even previous generation HPCs that relied on mainframe and supercomputers, they can also scale, right? It's not impossible, but it's practically infeasible depending on the cost and the overhead of maintenance and management that you will incur, right? Computer clusters will also increase the availability. It will increase the notion of fault tolerance, which means that in the event of a failure, your infrastructure is still functional, right? It will also enable the factor or the feature of what is known as modular growth that kind of again feedbacks into scalable performance. Okay, so here we can see that these are all individual pieces and workstation. If I want to doubly scale these computer cluster, this 4-set computer cluster, 4-device computer cluster, then all I need to do is acquire 4 more different machines, right? And that is easily doable. Okay, yes, Rahul?
Professor, just curious. So is fault tolerance and disaster recovery service both fall under the same umbrella or it's different?
No, so fault tolerance is the notion, and within fault tolerance, there is different techniques of fault tolerance, okay? Within those techniques, one of those techniques is known as recovery. Okay?
Okay, got it.
Okay. And then the final piece of the puzzle in terms of the benefits is that we are actually utilizing commodity hardware and software, which makes all of these possible, which makes modular growth feasible, which feeds back into scalable processing, scalable performance. Scalable performance is going to enable high availability as well as fault tolerance. So there is kind of like an interplay between the benefits of this. But these are not devoid of its own challenges, okay? In terms of research, when it comes to computer clusters or clustering, okay, the research falls into the computing subdomains of computer architecture and computer networks, okay, when it comes to research, all right? And some of the research challenges that you're going to face within this domain is basically how to perform faster communication, how to perform job scheduling and job allocation. Okay, in top of that, there is also a problem of allocation. Okay, and sometimes, or not sometimes, in the new day and age, there is another research domain which essentially is about service discovery, okay, which is also applicable to cloud computing as well. How do you develop techniques for single system images? We learned the fact that this block here, which is a middleware, actually enables the collective and cooperative functionality of these computer clusters, of all these pooled resources, right? The user who are using these computer clusters should not have this impression that there is a bunch of computers underlying the architecture, right? They should not be aware of that. They should not get that feeling, all right? So that is a research issue, is how do you develop good or very efficient and effective single system images? And then finally, how do you ensure high availability? Okay, High availability is an issue that kind of relates back to fault tolerance as well. That is, how do you develop good fault tolerance with respect to your particular system architecture? Okay, so now what are the different design objectives when it comes to designing computer clusters? Okay, so these design objectives can be classified into 6 different fields. All right, first one, of course, you're going to see this more very frequently. Okay, there is no escape from that. I know we have been talking about this again and again, but we will keep on talking about this probably throughout the end of the course as well. We have to make sure that whatever computer cluster architecture that you develop is scalable. We have to talk about packaging. Okay, then we have to talk about control, homogeneity, programmability, and then security. So let's look at these individually to better understand what are the requirements.
Oh, this is office hours for his other class, I think.
Okay. Hey, Ryan.
Sorry about that.
All right. So, so the first one is scalability. Okay. So scalability basically relies on modular growth. I'm not going to keep on harping about scalability again and again. You get the whole idea. Scalability is still a non-trivial task. If you're taking 100 of uniprocessor nodes and you're trying to scale up to 10,000 plus multi-core nodes, the whole development of that architecture is very challenging. Okay, you have to keep in mind. And what are the bottlenecks or the limitation that you face in terms of scalability? But the first one is the hardware constraint. That is, there is only so much of interconnectivity that you can support on one semiconductor chip, right? You cannot go beyond a certain level. So the multi-core chip technology is one of the major bottlenecks when it comes to scalability, right? Because if you remember, scalability directly feeds into parallelism. And parallelism is directly supported by MPP architecture, which is supported by multi-core chip technology. So if the chip in itself is limited in terms of hardware as to how much interconnections that it can support, then that will kind of have a cascading effect going back into whether or not you can support high level of scalability. Okay. The next challenge is basically how do you design your network? Okay, how do you interconnect all of these different computers, and how do you make sure that this interconnection is very efficient? So this basically goes into routing problems. Okay, that is the issues with respect to routing. What kind of routing topology is more suitable for your application? Should you use a mesh network? Should you use a bus network? Should you use a star network, and those kind of things? So that is coming from basic computer networks, right? Then we have packaging method. Okay, how do you package these computer clusters, right? Where do you store these PCs and workstations? How do you connect to them, right? Where do you keep them in a geographical region? So we're going to talk about that soon, all right? And then power consumption is also an issue. If you think about it, all the Bitcoin, this Bitcoin mining and all of these different technologies, they're using all of these computer clusters that consumes very heavy electricity, right? And that leaves a very huge carbon footprint, right? So how do you address that? If you have data centers in which you have all of these different clusters of hundreds and thousands of computers just packed together, right? Then how do you use, or what type of cooling methods do you use? Because that again is going to use power consumption as well. So how do you keep them effectively cooled off, right? Because if they get overheated, these systems are going to degrade faster than their lifetime, right? Other issues that you have is the issues of memory wall, the time that it takes to perform disk input output, and the latency that it creates. All right, so anybody has any idea on what a memory wall is? What is the most expensive operation in a PC or in any computer? Let's start with that question. Let's lead with that question and let's get into memory wall.
Maybe system booting.
Let's say we have booted and everything in your system is running. What do you do after that? Which operation takes the maximum amount of time? All right, before I go there, I would actually like to discuss something on a graduate level. Help me draw the architecture of a virtual computer. Not a virtual computer, but help me draw the architecture of a computer. A hypothetical computer architecture. What are the different components? What do you have? Tell me one by one. Think about it. Everybody uses computers. Have you ever thought what is the basic architecture of a computer? The fundamental architecture.
You have a CPU.
Okay, so CPU, let me write that down. So I want to do it a bigger unit. So you have the CPU and then?
Memory.
Memory.
Yeah.
Okay, so you have memory and then?
Like RAM and ROM.
Processor.
Different kinds of memories.
Okay, processor, we can keep it inside of this.
IO
Hard
devices.
drive.
Yeah.
Say that again.
Hard drive storage space.
Okay, so you have secondary memory.
And you
IO.
have a bus, data bus.
A data bus, okay, data bus, processing bus, that kind of interconnects everything.
Mhm.
So
you
we
have
will just say process communication interface, and then you have a data bus as well. And then somebody said IO, so we will just say peripherals.
Yeah, and then you have, I don't know, are we talking about software aspects as well? Like
That's all right. I think we are good for now. The basic architecture. Okay, so this is basically persistent storage. So that's where you were saying HDD and stuff like that. And this we will call primary memory, okay, which will host our RAM, okay, and stuff like that. So this whole thing will be inside a single unit, okay? And then I want to further break down the CPU into 2 more units. Can somebody tell me about that directly from computer architecture? CPU is the central processing unit, but the underlying computer hardware architecture of CPU is broken down and supported by 2 major units. What are they?
Motherboard.
Register.
Control units as well.
Control unit, and then one more.
And you have
Come on. Arithmetic and logic unit.
Yeah, logic unit. Yeah. Okay.
Logic unit, yeah.
Okay, so essentially that is what a computer is. It helps you do a bunch of computing operations, which is either in the form of arithmetic and logic. Go back to programming. What do they teach you in programming right after variables? How to write expressions. Expressions are basically composed of arithmetic operators and then logical operators. From there, you go into decision making and then loops, right? And then from there, you go into data structures. Okay. Once you get an idea of data structures, you learn about algorithm design and analysis and blah, blah, blah. That's how you develop your core knowledge, right? Where is that coming from? Because that is coming from this whole architecture, because it supports it, right? All your adders, all your gates that is implemented, they are here. So this is the chip, essentially, that supports it, right? And the execution of this chip happens within the primary memory, right? So what is the most expensive operation within this architecture? Expensive, when I say expensive, in terms of computing terms, I'm talking about time or latency.
Accessing memory, like read-write operations.
Read-write operations, right? So we are going to call that disk IO, disk input-output. Okay, not the peripheral operations. This has its own time, yes. But in terms of an execution of an application that runs within this computer architecture, the most expensive operation is disk IO. And within disk IO, there is a specific operation that is known as seek time, which is what makes this whole process the most expensive. So the issue of memory wall is basically this difference between the speed of what happens within the primary memory, okay, and the secondary memory. So this distinction that you see, this boundary, this is known as a memory wall. The difference in speed between these 2 segments is what creates the limitation in terms of speeding things up, right? And we don't have a solution. We do have a solution right now, right? What is the solution right now in order to reduce this memory wall? Right now we are using it. all the computer architectures that is coming out right now, your laptops, your MacBooks, Mac Airs, and stuff like that, they're using SSDs. Okay. So instead of using hard disk drives or old hard disk drives right now, the secondary memory is now being replaced by this solid state drives. So what solid state drives means that these memories are non-volatile, similar to what it's non-volatile, but it has the performance of your primary memory. So that means when you turn off the power to your machines, it kind of retains the state of the memory that was previously there. So this memory wall is kind of being breached to a certain degree. But SSDs are very expensive when it compares to HDD. So now, if you look into a computer which has an SSD of, let's say, 512 GB, right? It's very costly. It kind of takes you around in the domain of $1.2 thousand, right? If you're looking into your MacBook Pros and stuff like that, which are very performance efficient, right? And if you want a 1 TB of SSD, that is going to go around $2,500. If you take off the brand of Apple, then probably you will get $1,500, but still, that's very expensive, right? So this is what this whole problem or this whole limitation of memory wall, disk IO, and latency is kind of implying, okay? So let's talk about packaging. What does packaging means? When it comes to computer cluster packaging, you have two options. One is compact packaging, and the other option is slack fashion, okay? So when you have compact packaging, all the nodes are sitting in this one or more racks in a given room, right? Similar to all these hacker movies that you see, and this guy is like breaking into this room, and then there is this rows and rows of like computer racks just sitting there, and you have servers sitting on top of them. That is basically a compact packaging cluster, right? All of them, they are basically without any peripheral devices, just interconnected to the network, and they're sitting in a single room, all right? Most of the times when you have packaging like this, the administrative access is from a centralized fashion, okay? There is somebody from a centralized location who is administering all the management tasks for these compact clusters. In contrast to compact clusters, you have slack clusters, okay, where you have the individual nodes. So an example of slack clusters, you can think that if we all decide in this class to interconnect our computers together, so that will be an example of a slack cluster, right? We all have our own devices, right? Everybody, the ownership of these devices, of these nodes, are separate. They are connected to their own peripheral devices. You can connect whatever amount of peripherals that you want. These may be located across different rooms. This can be located across different buildings. This can be located across different regions, right? So that is basically slack packaging. And what is important to keep in mind here is that even though slack clusters are more distributed when it comes to compact clusters, you have to keep in mind that the communications will take a hit in terms of the overhead, depending on what kind of communication or what kind of packaging option that you use, right? So compact clusters may not give you much flexibility in terms of deployment, right? But it will give you a good latency, right? You can connect them using a very high bandwidth network interconnectivity because it is kind of hosted in a single location, in a single room, for that matter of fact. But then slack of clusters, you have to connect using Ethernet and Internet protocol technology, which is inherently slow when it comes to local connections, okay? So that's the packaging. Control, you can have centralized control, you can have decentralized control, okay? If you have centralized, then all of the nodes are owned, controlled, and managed and administered by a central operator, whereas decentralized have individual owners. In terms of the interplay between these different features, you have to keep in mind that compact clusters are typically centralized, whereas slack clusters can either be centralized or be decentralized, okay? Homogeneity, you can have either homogeneous clusters, okay, which means that all of the computer nodes that are present in the clusters belong to the same platform. They have the same processor architecture. Probably they're all using x86, for example, and Windows operating system. And at times they can be supplied, that is, the hardware can be supplied from the same vendors as well. A case in point for these homogeneous clusters are basically all the machines that you have in your computer labs at engineering center. Some of them are supplied by Dell. Then you have this one lab on the 5th floor, which is all Mac OS, right? So they're supplied by Apple. On the contrary, you can have heterogeneous clusters, which is the exact opposite of homogeneous, where you will have different platforms. But the challenge in heterogeneous clusters is basically how are you going to perform interoperability? Okay, if there is a different proprietary issue, if there are different platforms, then an application that is designed to run on a specific platform cannot be migrated to another platform. That is going to cause some issues, right? And as a result of that, the notion of what is called load balancing is going to take a direct hit because of interoperability challenges within heterogeneous clusters. So that is something that you have to be mindful of. Finally, you will also have security issues, right? So all these clusters need to communicate. The devices, the nodes of a cluster need to communicate with each other. And if you are communicating with if the devices are communicating with each other, then there are two different options for you. One is the communications are exposed, okay? And by exposed, we don't necessarily mean that you don't have any kind of encryption. That is not what we are trying to say. By exposed means that you are using the TCP/IP protocol or Internet Communication Protocol, right, in order to allow these devices to communicate with each other. So the moment you use IP routing, right, that means that the internet has access to these cluster machines as well. So as a result of that, the devices or the nodes that are outside of the cluster can also ping these machines, right? Unless, of course, it's a separate line of discussion. If you develop firewall policies, network access policies, then you can stop some of these connectivities, right? But what this particular concept of this particular feature is pointing to is the fact that the connectivity is possible. And that is what exposing the communication means, right? And that has a direct impact on security, because now you have to come up with efficient security schemes in order to connect, in order to make sure that your devices are secure, your devices have privacy, right? The other thing is that if you're using TCP/IP, TCP/IP essentially uses Ethernet, right? Ethernet has an overhead in terms of latency. It's not that fast unless you opt for it. But even you opt for it, there is only a certain amount of speed up to which you can go. Probably right now you have Gbps speed, right? But that has an interplay with cost of acquiring that kind of services, right? Nobody in general goes for Gbps services for day-to-day clusters, all right? We kind of know that. So that is another problem, that latency might have an overhead if you're using TCP/IP. In opposition to exposed communication protocols, you have the enclosed communication protocol. Now, the problem is there is no standardized enclosed communication protocol for intra-cluster communication. That is one of the major challenges that is present when it comes to enclosed, and that is why people like to just use exposed, because the protocol or the infrastructure already exists for it, right? So if you have to, or if you want to use enclosed communication protocol, you have to develop your own communication protocol that is specific to your own architecture and deployment, right? So that is what you have to keep in mind. Another notion within computer clusters is the idea of dedicated and enterprise clusters, okay? So any kind of deck side rack within a central computer room is an example of dedicated clusters, which is developed using homogeneous computers, okay? It is managed by a single administrative group, and it is what is responsible for substituting the traditional mainframe and supercomputers, right? It can execute both interactive and batch jobs as well. Whereas if you have enterprise clusters, then you're using something along the lines of a Slack cluster, okay, a Slack packaging. That is, the whole idea behind creating these clusters is to effectively utilize the idle resources of the nodes. Remember the application that we were discussing where my computer is running just 3 applications. So probably it is using more or less 5 to 10% of my CPU capability. 90% is empty, right? What if I want to overutilize those resources? Well, then I can create what is an enterprise cluster in that particular situation, right? So all the nodes are going to be heterogeneous in nature. They will be geographically distributed, may or may not, right? And there can be a singular cluster administrator. So that means that you can have a centralized point of administrator, or you can have a distributed administration as well. That is, you can have subsets or subnets of different clusters being managed by different entities, right? But keep in mind that the administrator doesn't have much control over these nodes, because these nodes have different ownership entities, and the local jobs are going to take priority over the enterprise job. Okay, so that means if I connect my computer to a cluster, if I run an application on my computer, that will take priority over a job request that you might have submitted to my computer. Okay, but the whole goal is to make sure that you utilize the resources. All right, so we'll stop here for today. And in the next class, we will continue discussing the different fundamental cluster design issues that we have within the domain of computer clusters. And we will probably extend our discussion into the virtual machines, okay, once clustering is done. All right, because that is essentially the next effective step that leads us towards more and more closer towards cloud computing. We will talk about virtual machines, and then we will talk about data centers, automating stuff. That will give us a complete knowledge moving into cloud computing and understanding the cloud computing architecture. Okay, so I'm going to wrap up here. And if there are any lingering questions, I'm going to take that. Otherwise, you're all free to sign off.